Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 3 for October 2022. Let us begin with the first question. Question 1. In the test for sulfate ions, an acid is added followed by aqueous barium chloride. Give a reason why the mixture needs to be acidified. Acidification prevents the formation of white precipitates that will not be barium sulfate. For example, if there is a hydrogen carbonate or sulfite, there is a possibility of white precipitates being formed and confusing the result of the experiment. So acidification ensures that we get rid of this so that any white precipitate formed is due to barium sulfate. In the next part, identify by name or formula a suitable acid and justify your answer. Because they use barium chloride, I wrote hydrochloric acid should be used because it would not cause a precipitate with barium ions. Remember, all chlorides are soluble except those of silver and lead. The next part says, a student is given a sample of white crystals to test for sulfate ions. Describe how the test should be carried out. Include a positive result. So since these are crystals, we need to dissolve them in water. So dissolve the crystals in a small quantity of the ionized water, and then you add hydrochloric acid followed by barium chloride. And if you observe a white precipitate, then that is a confirmation that sulfate ions are present. Moving on. In part B, a student is given a solid known to be either sodium bromide or barium chloride. State the test you would carry out on separate solid samples of sodium bromide and barium chloride to show the cations present. Include the positive result for each cation. So here the cations are either sodium or barium. So we can do a flame test for both. You carry out a flame test, sodium is going to give a yellow flame and barium is going to give an apple green flame. So moving on down here, they say, state the test you would carry out on separate solutions of sodium bromide and barium chloride to show the anions present. So here the anions are going to be bromide, or we're going to have a chloride. All we need to do here is to use nitric acid followed by silver nitrate and then observe the color of the precipitate formed. So if it's a chloride, it's going to give a white precipitate, and if it's a bromide, it's going to give a cream precipitate. However, the white precipitate given with silver chloride is going to be soluble in dilute ammonia, but the cream precipitate with silver bromide will not be soluble in dilute ammonia, but it will be soluble in concentrated ammonia. So that is how you can distinguish between the two precipitates formed. So this brings us to the end of question 1. Let's continue to question 2. Question 2. Some antacid medications to treat acid indigestion contain magnesium carbonate, which is that a student investigates how much magnesium carbonate is in an antacid tablet. So the procedure is as below. They crush a 1.3 gram tablet to form a powder, then add the powder to 75 centimeters cubed of 0.2 mol per decimeter cube sulfuric acid. Then stir the mixture until the reaction is complete. Then make up to 250 centimeters cubed with distilled water. Then they titrate 25 centimeters cubed sample of the solution against sodium hydroxide to determine the number of moles of sulfuric acid that did not react. So the results are given in the table. We have the final rating, the initial rating, as well as the different titers which are RAF 1, 2, and 3. So the first question was complete the table. Completing the table was about finding the titer value. So it's just that minus that gives us that, and that minus that gives us that, that minus that gives us that, and that minus that, we get that. The next part says calculate the mean titer for the titration. The mean titer should be calculated using concordant results. If you try to calculate, you see that these 3 results are concordant, while this is not concordant with any of them. So we can leave this out and just use these 3. How do we know if results are concordant? We need to get a difference between them. If the difference is within 0.2, then they are concordant results. So this, that, and that are what I used here. I divided by 3 to calculate the mean titer, which is 12.20 centimeters cubed. So down here in part B, they say the equation for the titration reaction is as given here. Sodium hydroxide reacts with sulfuric acid to give us sodium sulfate and water. So they say calculate the number of moles or sulfuric acid that reacted with sodium hydroxide in the main titer using your answer from A to. So I found the number of moles using concentration times volume. We know this is the main titer, so that is the volume I used here. However, we need to go back and find the concentration of sodium hydroxide, and this is what we were given. So number of moles of sodium hydroxide are going to be concentration times volume, but this volume is in centimeters cubed, so I divided by 1000. If I multiply by 10 power negative 3, it's the same as dividing by 1000. To convert the volume into decimeters cubed and multiplying the two, I got this as my answer in moles. Now when we go to the reaction equation and look at the mole ratio between sodium hydroxide to sulfuric acid is 2 to 1, meaning using the moles of these, the moles of sulfuric acid are going to be half the moles of sodium hydroxide. So dividing this by 2, I got 1.525 times 10 power negative 4, which is roughly 1.53 times 10 power negative 4, and this was in the 25 centimeters cubed that was pipetted. Moving on. Here they say, calculate the total number of moles of sulfuric acid used at the start of the experiment. So to do this, we need to go back at the equation to see. They said add powder to 75 centimeters cubed of 0.2 mole per decimeter cubed sulfuric acid. So we're going to use this volume and that concentration to calculate the initial number of moles. So number of moles is concentration times volume, 0.2 times 75. Again, dividing this by 1000 to convert that to decimeters cubed gave me 1.5 times 10 power negative 2 mole. And that's my answer. The next part says calculate the percentage of magnesium carbonate in the antacid tablet using your answer to B1 and B2. You must show you're working clearly. So here they've given us the equation. We have magnesium carbonate reacting with sulfuric acid to give us magnesium sulfate, water, and CO2. Here I started by calculating the moles of unreacted sulfuric acid. This is those remaining after reacting with one tablet. And we know previously we had that in 25, but I wanted to get that into 50. So I multiplied by 10 and I got this. Now to find the number of moles of sulfuric acid that reacted, we need to go back to the initial moles, which were these. These were the moles of sulfuric acid that were put. So the initial moles minus the unreacted moles, which are going to be that. So the answer is going to be 1.5 times 10 power negative 2 minus 1.525 times 10 power negative 3. And I got this as my answer in moles. So when we look at this equation, we can see the mole ratio is going to be 1 to 1. So moles of magnesium carbonate in one tablet are going to be 1.3475 times 10 power negative 2 mole because the ratio is 1 to 1. Now I'm going to use these moles to find the mass. Mass of magnesium carbonate should be the number of moles times the molar mass, which is this number of moles times the molar mass we were given, which is that. So I got 1.1359 grams. And then the percentage of magnesium carbonate is going to be the mass of magnesium carbonate divided by the original mass we were given times 100. If I take you back to show the tablet was 1.3, so that is the original mass. So finally my answer was 87.4%, and that is the percentage of magnesium carbonate in the tablet. Next I say, give one possible reason for carrying out a rough titration. This is to approximate the endpoint so that towards the endpoint you can add drop by drop in order not to overshoot the endpoint. So it's an approximation to get the endpoint or to get a clarity of where the endpoint should be so that we do not overshoot it. And lastly here they say, phenolphthalein indicator was used in the titration. State the color change seen at the endpoint. Since we had the acid, which is sulfuric acid, in the conical flask, and the burette contains sodium hydroxide, it means phenolphthalein indicator in acid is going to be colorless, and at the end it's going to be pale pink. So that should be the answer. So this brings us to the end of question 2. Let's continue to question 3. Question 3. Precipitation reactions can be used to determine the formulae of compounds. A bottle has a torn label which shows that it contains a nitrate, and we do not know which metal nitrate is contained inside. So the procedure is as below. A technician dissolves a sample of 12.41 grams of the nitrate in the ionized water to make 100 centimeters cubed of solution. The technician pipetted 5 centimeters cubed of 1.5 mole per decimeter cube potassium iodide into each of the series of test tubes. Each test tube then had a volume of the nitrate solution added to it, as shown in the table. A cloudy yellow solution formed and the precipitate was allowed to settle. The height of the precipitate was then measured, and the equation for the reaction is given to us as that. So the results of the experiment are here in the table. We see the volume of the solution is increasing as we see the height of the precipitate increase. The first part says, plot the data on the grid. Now we know which one is the independent variable. It's going to be the volume of the solution that is changing, and then the height is going to be what we measure. So the height is going to be on the vertical axis, and the volume of the nitrate is going to be on the x-axis. So I used an appropriate scale based on the data that I was given, and my points were through here, there, that, and that. So the question asking me to draw a line of best fit is on the next page, so let me first go there. Here they say, state why the height of the precipitate becomes approximately constant. Now, if you go back to this reaction, we are reacting a metal nitrate with potassium iodide and observing the precipitate formed. If the precipitate stops increasing, it means one of these has been used up. Since this is continuously added, it means potassium iodide is used up because the metal nitrate is in excess. So here I say it, because iodide is finished, the metal nitrate is in excess. In part B, determine the minimum volume of nitrate solution needed to react completely with 5 centimeters cubed of potassium iodide solution. You must show you're working clearly. So to go back to the graph, I drew a line of best fit through this point and a line of best fit through the other points because, of course, this is an anomalous point. And then these two lines connected at this point, meaning at about 10 centimeters cubed of the nitrate, the reaction had stopped. So I used the volume to be 10 centimeters cubed. So my answer is 10.0 centimeters cubed. But the allowed answer should be between 9.5 to about 11 centimeters cubed. Then they say, calculate the number of moles of potassium iodide in each test tube. Number of moles is concentration times volume. And again, to find the components for potassium iodide, I want to take you back here. This is the information for potassium iodide, 5 centimeters cubed and 1.5 mole per decimeter cubed. So I'm going to use that. Number of moles is concentration, which is 1.5, times the volume, which is 5 divided by 1,000, and I get 7.5 times 10 power negative 3. The next they say, calculate the concentration of the metal nitrate solution in gram per decimeter cubed using the information given in the procedure. Concentration in gram per decimeter cubed is mass concentration, so it's going to be mass divided by the volume. So if I take you back here, the mass given to us is 12.41 and the volume is 100. So we're going to divide 12.41 by 100, which is divided by 1,000, so that this is converted to decimeters cubed, so that we can get our mass concentration in grams per decimeter cubed. So the key thing is 12.41 divided by 100 divided by 1,000, converting this to decimeters cubed. It gave me 124.1 gram per decimeter cubed as the mass concentration which is required here. You can see gram per decimeter cubed, so mass concentration. And down here they say, identify X by using your answer in B1, B2, and B3 to determine the MR of the metal nitrate. You must show or you're working. So here I rewrote the equation to avoid going back to the previous page. Now using the information I've already calculated, I wanted to use the moles of potassium iodide that reacted because we know that this got finished to find the number of moles of this that were reacted. And if we go back here, we can see these are the moles of potassium iodide. So since the mole ratio is 1 to 2, the moles of the nitrate should be half the moles of the potassium iodide. So it's going to be a half times that, which gave me 3.75 times 10 power negative 3 moles. So these are the moles of the metal nitrate that reacted. Now, the volume of the metal nitrate used was 10 centimeters cubed, you remember from previously. So the molar concentration is going to be number of moles divided by volume, which is that divided by this volume in decimeters cubed. And again, that is why I used 10 divided by 1,000, converting that volume to decimeters cubed. And this was my molar concentration. The next part was to find molar mass. Molar mass is equal to mass concentration divided by molar concentration. Since I already have the mass concentration here, and I've calculated the molar concentration, if you follow the units, molar mass is gram per mole, mass concentration is gram per decimeter cubed, molar concentration is mole per decimeter cubed. If these units are cancelled out, you get the units gram per mole, which is molar mass. So this is what I used, mass concentration divided by molar concentration, and I got 330.93 gram per mole. So this is the molar mass of the metal nitrate. And now since I know that nitrate is going to be nitrogen, which is 14, plus the 3 oxygens, which is 48, when you add them and multiply everything by 2, I'm going to subtract whatever I get from the total molar mass in order to find the component of X. So in the end, the total molar mass minus the component from twice the nitrate gave me 206.93. So using your periodic table, X is lead. Moving on. Here they say, deduce the ionic equation for the formation of Xi2 using your answer in B4. Include state symbols in your answer. Now this is the ionic equation, but down here I'm going to show you how I got it. Since we know X is lead, so we can know that lead nitrate plus potassium iodide gives us lead iodide plus potassium nitrate. This is aqueous, that is a solid, and that is aqueous. So I separated the aqueous. Here we have Pb2 plus, and here we have 2 nitrates. Here we have 2 potassium, and again 2 iodide. And on the other side, lead iodide is a solid, so I didn't separate it, but I separated the aqueous, so 2 potassium and 2 nitrate, and then they cancel out. So spectator ions like nitrate cancel out and potassium cancelled out. So I remained with Pb2 plus 2I minus, giving me lead iodide as a solid, and that is my ionic equation I wrote here. In part C, suggest why some of the precipitate heights may be above the maximum height expected. Assume there was no measurement error. The only reason as to why some would be higher is because not enough time was allowed for all the precipitates to settle down in order to be compacted enough. So I said because not enough time was allowed for the precipitate to settle. In part D, the metal nitrate is toxic. Draw the hazard symbol that should be displayed on the bottle. This is the hazard symbol for toxic. This looks like bones, and then we see a skull. So if you had drawn it like this or something similar, you would get 4 marks for this. And again, be very careful. These days they're bringing a lot of questions about drawing hazard symbols, so you have to try and make sure you fully understand how to draw them in order to get 4 marks. So this brings us to the end of question 3. Let's continue to question 4. Question 4. Propan-1-O, propan-2-O, and 2-methyl-propan-2-O are all alcohols commonly used in school laboratories. Acidified potassium dichromate 6 is used to oxidize alcohols. State the color change seen when an alcohol is oxidized with acidified potassium dichromate. If oxidation takes place, then the color changes from orange to green. The next part says, draw a label diagram of the apparatus that is required to prepare and collect a sample of propanal by heating propan-1-O with acidified potassium dichromate. If propan-1-O is heated with acidified potassiam dichromate here, then it means oxidation is going to occur, and then the aldehyde is going to be collected. So I included anti-bumping granules. There is a source of heat, and then a reaction is going to take place here. The aldehyde is going to evaporate, go through the condenser, and then collect it here. You have to position the condenser in a slanting manner, and then water has to come in here and then leave out at this point. The condenser has to be labeled as well as the collector. So down here they say, an electric heater may be used to heat a sample of an alcohol with acidified potassium dichromate. State why an electric heater should be used rather than a Bunsen burner to heat these reaction mixtures. Because alcohols are flammable and the alcohol is a reactant here, you want to avoid accidents, so it's better to use an electric heater that does not have an open flame. Moving on. Here they say, state why there is no reaction when 2-methyl-propan-2-O is heated with acidified potassium dichromate. This is because 2-methyl-propan-2-O is a tertiary alcohol, so it cannot be oxidized. That is why there will be no observable change. And next they say, identify by name or formula all the possible oxidation products of propan-1-O and propan-2-O. Propan-1-O is a primary alcohol, so it's going to be oxidized to an aldehyde, which is propanal, and to propanoic acid, which is a carboxylic acid. Propan-2-O is a secondary alcohol, so it's only going to be oxidized to a ketone, which is propanone. Next they say, Give a further chemical test and a positive result for each of the oxidation products of propan-1,0. So propanal, which is one of the products here, propanal, we will use Benedict's or Fehling solution, and a red precipitate is formed. If you choose to use Tollens reagent, then a silver mirror is going to be formed. Now please remember you have to use one of these, not both of them, because they're testing for propanal and they're both giving a positive test. Now for the other product, which is propanoic acid, you can just add sodium carbonate, and if there is effervescence observed, then that is a confirmation that it is a carboxylic acid, which in this case is propanoic acid. So this brings us to the end of question 4 as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.